In our last video on mass driver, we looked at the basic rocket equation and its implications for spaceflight. If you haven't seen that one yet, I recommend watching it first to better understand the relationships in this video. This video is about single stage to orbit, SSTO. So far, this is only a dream of rocket scientists and is difficult to achieve with today's technology, at least if you want to do it without nuclear propulsion and launch from Earth. From the lunar surface, on the other hand, it would be easy, as SpaceX's Starship will at least be able to launch single stage from the surface of Mars. Nevertheless, there have already been several concepts for single-stage rockets and spaceships, yet none of these concepts reached production readiness and are at prototype status at best. It's not difficult to reach space on a suborbital trajectory with a single-stage rocket. The first man-made object to reach space at an altitude of 84.5 kilometers was a V-2 rocket developed by Wernher von Braun on October 3, 1942. 2 years later, a single-stage V-2 also crossed the Kármán line, the official boundary to space, at an altitude of 100 kilometers. The difficulty lies in entering an orbit because a speed of 28,000 kilometers per hour is necessary for this. The X-33 of Lockheed Martin's Skunk Works was the most ambitious project and should serve as a scaled-down technology demonstrator for the formerly planned successor of the space shuttle, the Venture Star. This glider was to take off vertically and land horizontally. But unlike the space shuttle, it was to have no side boosters. However, this project was cancelled in March 2001 due to the cost overruns, particularly with the liquid hydrogen LH2 fuel tank made of composites. Although engineers also developed a conventional aluminium tank to solve this problem, NASA, represented by Ivan Beakey, insisted on the innovative composite tank in a US House of Representatives hearing on April 11, 2001, to the astonishment of Lockheed Martin. By then, 85% of the prototype had been assembled, and over 95% of the individual parts had been manufactured. This space shuttle would also have been equipped with Rocketdyne's XRS 2200 linear Aerospike engines, which are more efficient than conventional bell-shaped rocket nozzles because they can provide maximum thrust at different altitudes rather than just a specific altitude. This is made possible by adapting to atmospheric air pressure. Such an engine is lighter and requires less fuel. Above all, this would bring a further weight saving. The impact on a rocket's fuel costs is negligible compared with other costs. It's interesting to note that in 2004, competitors succeeded in using a new manufacturing process to produce a working hydrogen tank made of composite materials. As a result, the US Air Force was ready to resume work on the X-33 project, but the US government stopped this. Currently, there is Skylon, the British project of the company Reaction Engines, which the British government supports, the European Space Agency, and since 2017, also by DARPA. This unmanned space shuttle could reduce the price per kilogram for transport into orbit to less than €1,000. What's special about this project is the synergistic air-breathing rocket engine Sabre. Initially, the engine would suck in air from the atmosphere and be powered by liquid hydrogen. Only at an altitude of 26 kilometers at a speed of Mach 5.5 would liquid oxygen be injected into the engine, accelerating the vehicle to Mach 25. Skylon would thus be able to take off like an airplane and enter an orbit around the Earth without any other aid. After re-entry, land like a conventional airplane on any runway, protected by ceramic composites. However, it's currently assumed that such an engine will not be operational before 2025. There's recently been a technological breakthrough that increases the feasibility of single-stage concepts. In 2017, scientists at Harvard University succeeded for the first time in producing metallic hydrogen on Earth, albeit at great energy expense. Until now, it's only existed in the lower layers of Jupiter, where gigantic pressures prevail. Due to the high amount of stored energy, metallic hydrogen could be used as rocket fuel in the future and revolutionize space travel, if we succeed in producing it in the laboratory and on an industrial scale. What do you think? Write your opinion in the comments.